So elliptic equations is amenable to very similar analysis if the kappa is a constant, right? So if there is no nonlinearity. So do we all understand what linearity means? I mean, we may all understand, but like, let me just describe to you again in the case of a partial differential equation. Okay, so in a partial differential equation or in anywhere, linearity means if you increase the input by a factor of 2, the output would increase by a factor of 2. You increase the input by a factor of n, the output would increase proportionally by a factor of n. Not only that, if you have one input we call A, another input called B, you get output, let's say, called X and Y. Okay, now if you make the input actually equal to A plus B, now the output would be exactly equal to X plus Y. So that's linearity. So its linearity means it's linear with respect to a constant multiple of input. You get output that is also the same constant multiple. It also means addition, right? Additive. So the phrase linear superposition means if you add two inputs, the output would be the sum of the two respective outputs. So that's linearity. Okay, here is the equation that is linear. Let's consider f as an input, w as output, right? So if you want to solve the equation, you have to know what f is, right? The solution is w. So f is the input, w is output. If you make f twice as large, the solution would still be satisfied as long as you make w twice as large, right? So that's kind of a proportional argument, one of the ingredients of linearity. Again, if you have f1 and w1 satisfying this equation, also you have another pair, f2 and w2 satisfying this equation. If you add these two equations together, you're going to see that w1 plus w2 is the solution to the equation whose input is f1 plus f2. So this equation is linear. It's not the case if k actually depends on w. If k depends on w, the argument goes away, right? Okay, so that's a linear equation. And for linear equations, for linear partial differential equations, Fourier analysis usually works its way pretty well. So I'm supposed to end the lecture in 1 minute, but let's just say f is equal to a summation of a Fourier series. I'm just call it ak and I times 2 pi kx. So this is a complex expression that is the same as the sine and cosines of the last lecture. And here k has go to minus infinity and infinity. Through Fourier's analysis, you're going to say that w can be written exactly as the same thing, but I have ak divided by 2 pi k square times e to the I pi k x. Okay, you can repeat the same analysis at home. It's basically the same as what I did on the last page. But what you're going to see is that w is going to be significantly smoother than f. Why? Because if you compare f and w, yeah. Huh? It's integrated twice. That's one explanation. Another explanation from the Fourier series, you see the high frequency components get decayed by 2 pi k squared, right? Huh? Oh, and kappa, yeah, thank you. The higher frequency the signal is, the larger the ratio is between f and w, right? That's why w is going to be smoother. Okay, so that's elliptic equation. There is another final type of equation, a hyperbolic equation. We want to analyze. That's the case when u is not 0. We are going to leave that to the next lecture. All right, so see you next Monday. And before I end, I'm going to say the self-assessment project is also due on Monday. So we are going to grade it if you submit it on Monday. We are not going to grade it if you don't. So that's it's not going to impact your grade. And have a good first week at MIT for those who are new.